For most of human history, the birth of new ocean floor could only be reconstructed after it happened. Scientists mapped underwater ridges, measured tectonic plates drifting apart, and studied lava that had already hardened into rock. But they had never placed enough instruments in exactly the right location to watch the complete process unfold on the deep seafloor. Then, only 2 months after a new observatory was installed in the southern Indian Ocean, the ocean floor began tearing open beneath it. The event started on April 26, 2024, along the southeast Indian Ridge between Antarctica and Australia. Within days, parts of the seabed moved horizontally by meters, the floor of an underwater valley dropped by more than 4 meters, and magma forced its way through the crust. Over roughly 16 days, around 160 million cubic meters of lava poured onto the seafloor. That would be enough molten rock to fill about 64,000 Olympic swimming pools. Scientists had not simply detected an underwater eruption. For the first time, they had recorded a mid-ocean ridge spreading event using seismic sensors, acoustic distance measurements, pressure instruments, and detailed maps of the seabed at the same location. The result provided a rare view of how Earth creates new crust. Mid-ocean ridges form the longest mountain system on the planet. Together, they stretch for approximately 65,000 kilometers across the ocean floor, wrapping around Earth like the seams on a baseball. They mark boundaries where tectonic plates move away from one another. As the plates separate, hot material rises from the mantle. The decrease in pressure allows part of that material to melt. Magma then moves upward through fractures, cools, and becomes new oceanic crust. In a simple diagram, this process appears almost continuous. 2 plates slowly move apart while magma steadily fills the gap between them. But the real ocean floor does not move so smoothly. At the section studied by the research team, the average spreading rate is about 63 millimeters per year. That is roughly the speed at which a human fingernail grows. If the crust moved at that rate every day, the process would be almost impossible to notice without precise instruments. The new observations reveal a different pattern. A ridge can remain relatively quiet while stress accumulates for decades. Then, within hours or days, it can release many years of movement in one violent episode. It is similar to slowly stretching an elastic band. Most of the visible change happens only when the stored tension is suddenly released. The scientists designed an observatory called OICHEGODAMS to capture exactly this type of event. In February 2024, they deployed it across an active segment of the southeast Indian Ridge and the nearby Amsterdam Transform Fault. The location lies near the St. Paul and Amsterdam Volcanic Plateau, a remote region surrounded by thousands of kilometers of ocean. It is difficult to reach, difficult to monitor, and hidden beneath roughly 2 kilometers of water. The system included 5 autonomous hydrophones that listened for low-frequency sounds produced by earthquakes and volcanic activity. 15 acoustic transponders were placed on the seafloor to measure changes in the distance between different points. A bottom pressure recorder detected vertical movement by measuring changes in the weight of the water above it. The transponders functioned like an underwater measuring tape. They repeatedly exchanged sound signals, and the travel time showed whether the seabed between them had stretched, contracted, or shifted. Then the team left the instruments alone. They expected that they might wait years before anything significant happened. Instead, the ridge began moving 2 months later. At 1956 UTC on April 26, the hydrophones detected several small earthquakes in the central part of the underwater valley. 13 minutes later, a magnitude 4.9 earthquake occurred beneath the ridge. The seismic activity then began traveling along the valley. First, the disturbance moved more than 8 kilometers toward the southeast. Minutes later, another sequence moved roughly 9 kilometers in the opposite direction. The signals traveled at approximately 2 to 3 meters per second. This moving pattern was an important clue. Earthquakes were not simply occurring randomly along the ridge. Something was forcing its way through the crust. The researchers concluded that magma was opening long vertical cracks known as dikes. Imagine pushing a blade into a block of soft material and forcing the 2 sides apart. A dike behaves similarly, except the blade is molten rock rising from a deeper magma reservoir. As the magma moved outward, the pressure instrument detected the seafloor dropping. During the most intense phase, the valley floor sank at an average rate of about 5 centimeters per minute. Within less than an hour, it had dropped approximately 1.2 meters. The sinking continued more slowly over the following days, eventually reaching about 4.2 meters. The collapse was not caused by the entire crust falling into an empty cavern. It was the surface response to a magma reservoir below losing material. The underground reservoir was deflating. A useful comparison is a partially inflated air mattress. Remove air from inside and the surface sinks. Beneath the ridge, magma drained from a broad reservoir into narrow dikes and toward the ocean floor. As the reservoir lost volume, the rock above it moved downward. At almost the same time, the acoustic transponders recorded major horizontal changes. Some distances increased by more than 1 meter. Others shortened as instruments moved toward the center of the collapsing area. By combining these measurements with computer models, the researchers estimated that the event produced approximately 2.1 to 4 meters of total horizontal extension. One plausible model placed the extension near 2.4 meters. At the normal annual spreading rate, creating that much separation would require around 38 years. During this event, decades of plate movement were compressed into a matter of days. But the most surprising part was how much of the movement occurred without producing large earthquakes. Scientists have long recognized a puzzle called the seismic moment deficit at mid-ocean ridges. The plates are clearly separating, but recorded earthquakes do not release enough energy to explain all the measured movement. The new observations suggest where part of that missing motion may be hiding. As magma entered the crust, it pushed faults and rock blocks gradually rather than breaking all of them through sudden earthquake ruptures. This movement is described as aseismic slip. The ground moves, sometimes by meters, without generating the strong shaking normally associated with such displacement. The ridge was not silent, but earthquakes recorded only part of the transformation. After the magma intrusion slowed, nearby transform faults became more active. These faults connect different sections of the spreading ridge and accommodate horizontal motion between them. A magnitude 5.9 strike-slip earthquake occurred on the Amsterdam Transform Fault shortly after the dike stopped traveling northwest. The timing suggests that the magma intrusion changed stress across the wider fault system and triggered movement beyond the central volcanic valley. The eruption itself was reconstructed from several clues. The bottom pressure recorder detected rising temperatures near the seafloor, suggesting that hot lava had reached the water. Hydrophones also recorded thousands of short, energetic sounds produced when molten rock interacted with cold seawater. More than 2,150 of these acoustic events were detected by at least 3 hydrophones before activity largely stopped on May 12. This indicated that the main eruption lasted approximately 16 days. When researchers returned in 2025, they remapped the seafloor and compared the new terrain with maps made before the event. The difference was dramatic. New lava covered multiple sections of the valley. Some deposits were more than 90 meters thick. One major patch extended for about 4 kilometers along the foot of a valley wall. Altogether, the researchers estimated that between 148 and 160 million cubic meters of lava had erupted. The new crust did not form as a thin, perfectly even layer. Magma traveled through different pathways, erupted along parallel lines, and accumulated into thick, irregular flows. This matters because abyssal hills cover much of the ocean floor. These repeating ridges and valleys preserve a record of how magma and faults have repeatedly reshaped the crust over geological time. Before this study, scientists understood their general origin but lacked direct observations showing how individual spreading events combine fault motion, collapsing magma chambers, dike intrusions, earthquakes, and silent movement. Now they have watched one of those building episodes happen. The discovery does not mean a dangerous crack is moving toward a continent. This event occurred at a normal divergent plate boundary deep in the ocean. It did not create a giant tsunami, split the planet, or signal an unusual global disaster. It was important because it exposed an ordinary planetary process that is usually hidden. Most new crust on Earth forms beneath the ocean. Old oceanic crust eventually sinks back into the mantle at subduction zones, while new crust emerges along spreading ridges. The surface of the planet is continuously destroyed and rebuilt. From a human perspective, continents and oceans appear permanent. From a geological perspective, they are moving parts in a recycling system. The observatory was also extraordinarily fortunate. Seafloor spreading events at a specific ridge segment may be separated by decades. The instruments were deployed only 2 months before the eruption began. Had the event occurred a year earlier, scientists would have detected distant earthquakes but missed the detailed movement. Had it happened after batteries failed or instruments were damaged, the complete sequence might again have remained invisible. Instead, sensors were positioned directly across the opening crust. They recorded the first small earthquakes, the migrating magma, the rapid collapse of the valley, the horizontal separation, the activation of nearby faults, the eruption sounds, and the final lava deposits. For the first time, researchers did not have to infer the full story from hardened rock alone. They watched Earth open a wound in its crust, fill that opening with molten material, and create a new piece of ocean floor.